Okay, let's talk about a problem that really pushes our traditional data tools, right to their breaking point. It's this. When you move from these nice, neat tables to the messy, tangled networks of the real world, how in the world do you follow a chain of connections that goes layers and layers and layers deep?
Seriously, think about it. If you're a pro with SQL, you can probably write a query to find a friend of a friend. Sure, that's a couple of joins, but what about 4 levels deep, or 10? The query just gets absolutely monstrous and fast. It's basically unmanageable.
And this really gets to the heart of the problem. Relational databases, they are fantastic for storing things, for storing entities, but they get really clumsy when you want to focus on deep, complex relationships. Every single step you take deeper into that network requires another self-join, which gets super slow and just becomes a nightmare to write and maintain. Graph processing, on the other hand, well, it's built for exactly this kind of problem.
To solve this, we really need to step beyond the world of table joins. We have to start thinking in connections.
This right here is the fundamental mental shift you have to make. Instead of focusing on, say, a table of users and another table of posts, graph processing is all about the relationships, the friendships, the likes, the shares. It's all about the lines connecting the dots, not just the dots themselves. That's the key.
So, how do we tackle a massive, crazy complex graph problem? Well, not with one giant scary query. We do it by thinking in small, repeatable steps. We think in iterations.
I want you to imagine information just rippling across a network, like a wave. In each step, or what we call an iteration, every single point in our graph, we call these vertices, it just looks at its immediate neighbors. That's it. It gets a little bit of info, updates itself, and then passes some new information along. It's this beautiful series of tiny local computations that together solve a huge global problem. Now, this brilliant idea needs an engine to actually make it work, right? In a framework like Spark's GraphX, that engine is built around one single core operation. And this is it, aggregateMessages. This function is the workhorse. It's the thing that lets us actually implement this whole message passing idea. It lets every single vertex gather information from its neighbors, process all that info, and then update its own state. It's literally how the vertices talk to each other. The elegance of this whole approach is that it breaks down all that complexity into just 2 simple things that you have to define. First, what's the message you want to send along each connection? And second, how should a point on the graph combine all the different messages it receives? That's it.
Okay, let's make this way more concrete. What do these message sending and merging functions actually look like? Are they complicated?
Well, let's imagine the simplest possible message you could send. For every connection in our network, we can just send a message, let's say the number 1, to its destination. It's kind of like every person just tapping their friend on the shoulder and saying, 1. Super simple. And here's the second part, merging those messages. When a vertex gets a whole bunch of messages, we just need to give it a rule for combining them. If the messages are just numbers, we could simply add them all up. So if you get tapped on the shoulder 3 times, your new value becomes 3. Easy enough.
Now, let's put those 2 simple ideas together for a second. What if we send a 1 not to the destination, but back to the source of every connection, and then we just sum up all the messages? In one single operation, boom, we've just calculated the out degree, the number of outgoing connections, for every single vertex in the entire graph. Think about how hard that would be in SQL. That is the power of this approach.
Okay, so a single operation is pretty cool. I'll give you that. But the real magic, the really amazing stuff, happens when we chain these operations together, one iteration after another.
So let's try to solve a more complex problem. Imagine a big family tree, or any kind of hierarchy. For every single person in that tree, we want to find out how many generations they are from the oldest ancestor they're connected to. This is a classic graph traversal problem. Okay, here's our game plan. First, we're going to initialize every person in the tree with a value of 0. Then, in each step, every person is going to send a message to their neighbors. And that message is just going to be their current value plus 1. Then, each person looks at all the messages they received and updates their own value to the maximum number they see. And we're just going to keep doing that over and over until the numbers stop changing. So here we are, at iteration 0. As you can see, every person's distance value is set to 0. Now we hit go, and the first wave of messages goes out. Everyone sends their value, which is 0, plus 1 to their neighbors. The people who are the direct descendants of an ancestor, they get a message with a 1 and they update their value. All right, now in the next iteration, the process just repeats. The vertices that are now set to 1 send their value plus 1, so 2, to their neighbors. So now the grandchildren in this network, they get a message with a value of 2, and they update themselves.
You see the pattern here, right? It's like a wave of information just propagating through the entire graph. With each iteration, that distance value moves one step further away from the original ancestors. The vertices that have a value of 2 are now sending out messages with a value of 3.
After a few more rounds, everything stabilizes. The values stop changing, and that's when the algorithm converges. Every single vertex now holds the correct value for its greatest distance from an ancestor. And this system knows to stop, precisely because an entire iteration passed with 0 updates. It's done.
So step back and think about what just happened here. We took a really complex graph-wide question and we solved it by having each individual vertex perform a super simple task over and over and over again. That is the entire beautiful idea behind iterative graph processing.
And this whole approach, it scales to graphs with billions of connections. It's what's used to find the most influential people in social networks, to detect complex fraud rings, to power recommendation engines. So the real question is, what will you find when you can suddenly ask questions that are 10, 20, or even 100 layers deep into your data?
Hey, if this helped you think about your data in a new way, do us a favor and hit that like button. Share it with someone who you know is still stuck thinking in tables, and of course, subscribe for more deep dives just like this one. Thanks so much for tuning in.